prove that for positive integer p, combination of p1 equals to p. By definition, combination pk can be expanded as follows. Combination pk equals to p factorial over k factorial times p minus k factorial. And now we replace the value of k with 1. Since combination p1 is a positive integer number by definition, let's denote it as n. Let n element of natural number. Now we get n equals to p factorial over 1 factorial times p minus 1 factorial. We move the denominator to the left side. We get n times p minus 1 factorial equals to p factorial. P factorial is obviously divisible by p, hence n times p minus 1 factorial is also divisible by p. Therefore, p divide n, p divide combination p1. It is proven. By using binomial theorem, find 3x minus 4y to the power of 5. Using the binomial theorem, here x equal to 3x and y equals to negative 4y. Substitute the x and y as the theorem, where the combination of n r equals to n factorial over r factorial times n minus r factorial. We solve for it. After that, we simplify all the value. Therefore, 3x minus 4y to the power of 5 equals to 243 x to the power of 5 minus 1620 x to the power of 4y plus 4320 x to the power of 3 y to the power of 2 minus 5760 x to the power of 2 y to the power of 3 plus 240 x y to the power of 4 minus 32y to the power of 5. The following are about binomial and Pascal's triangle. How Pascal's triangle relates to binomial theorem. Pascal's triangle gives us the coefficient for an expanded binomial of the form a plus b to the power of n, where n is the row of the triangle. Give one example for your statement in A. Elaborate your answer. Let us use an example of a plus b to the power of 5. By using the binomial theorem, substitute the a and b as the theorem. And now we can obtain the binomial coefficient using the appropriate row of Pascal's triangle. This is the Pascal's triangle, and we know that the n value is equal to 5. So, for n equals to 5, the coefficient is 1, 5, 10, 10, 5, 1. Therefore, for a plus b to the power of 5 equals to a to the power of 5 plus 5a to the power of 4b plus 10a to the power of 3b to the power of 2 plus 10a to the power of 2b to the power of 3 plus 5ab to the power of 4 plus b to the power of 5.
Question 4. Let a divides b for a, b is an integer. Prove that a divides b, c. Okay, first, let b is equal to am. M is an integer, and c is equal to an. N is also an integer. So, by the definition of divisibility, BC is equal to A times MN. Okay, so this shows that A divides BC such that A, B, C is an integer. Therefore, it is proven. Note that Z is an integer. Question 5. Let A, B, C, and X be integers with A and B are not both 0 and X is not equal to 0. Prove that if GCD A and B is equal to 1 and X divide A, X divide BC, then X divides C. Okay, first, to show X divides C such that C is equal to XK, K is an integer. By the definition of divisibility, X is equal to XM, M is an integer, so we can note this as number 1, and BC is equal to XN and is an integer, we note this as number 2. Okay, by theorem 4 says that let AB is an integer, both not 0. Then A and B are relatively prime if and only if there exist integers x and y such that 1 is equal to AX plus BY. Okay. Since GCD AB is equal to 1, so by the theorem 4 we have 1 is equal to AX plus BY. X and Y is an integer, so we note this as number 3. By multiplying 3 with C, we can write it as C times 1 is equal to C AX plus BY. That is, C is equal to AXC plus BYC. We note this as number 4. Okay, next, by substituting 1 and 2 into 4, we have C is equal to XM times XC plus XN times Y. That is X times MXC plus NY. So this is equal to C is equal to XK. Note that K is equal to MXC plus NY, which is K is an integer. So by the definition of divisibility, we get X divides C. Therefore, it is proven. Note that Z is an integer.
So for the question 6, using mathematical induction, prove that 9 power n minus 2 power n is divisible by 7 for all positive integer n. So we continue. To show that the 9 power n minus 2 power n is divisible by 7 for all n is positive integer, we need to show that 1 is an element of set S, and for the second, let n equal to k, show that k plus 1 is also an element of set S. So for the first of all, show that 1 is an element in set S. So let n equal to 1, and we substitute n equal to 1 in the equation. So 9 power 1 minus 2 power 1 is divisible by 7. So we get 7 is divisible by 7. So which show that 9 power n minus 2 power n is divisible by 7 if n is equal to 1. So we can make sure that 1 is an element of set S. For the second property, let n equal to k. Show that k plus 1 is also an element of set S. So we substitute n equal to k. So we get 9 power k minus 2 power k is divisible by 7. So by the definition of divisibility, we can also write it in equation such as 9 power k minus 2 power k equal to 7m. So we transfer 2 power k to the right side and we get 9 power k equal to 7m plus 2 power k. So for the next step is we need to change k equal to k plus 1 in the latest equation. So we get that equal 9 power k plus 1 and minus 2 power k plus 1. We can also write it in terms of 9 times 9 power k minus 2 times 2 power k. So we substitute 9k 9 power k equal to 7m plus 2 power k into the latest equation and we get equal 9 times bracket 7m plus 2 power k bracket minus 2 times 2 power k, and we get that 7 times 9m plus 7 times 2 power k. So we factorize by 7 and we get 7 bracket 9m plus 2 power k bracket. So by the definition of divisibility, 9 power k plus 1 minus 2 power k plus 1 is divisible by 7. Then it shows that k plus 1 is also an element of set S. And the last one is 9 power n minus 2 power n is divisible by 7 because it satisfies both properties.
Question 7. Find all the solution xy to the following different equation, for which xy are both positive integers. The equation is 11x plus 13y equal to 369. For the solution, we need to using Euclidean algorithm to find GCD of 11, 13. First, we need to know our a and b. A must greater or equal to B, so our A is 13 and our B is 11. We need to using this formula A equal BQ plus R. Q is the most greater multiply below the value of A. Meanwhile, R1 is the remainder from A subtract BQ. We substitute A and B to the formula. 13 equal to 11, the greatest multiply is 1 plus remainder is 2. 11 equal to 2, greatest multiply is 5 and plus remainder is 1. We do this until we get 0 remainder. Then GCD 11, 13 is 1. The equation has solution since 1 can divisible by 369. To find x and y, we need to using backtracking. Our GCD is 1 equal to our b is 11 minus 2 multiplied by 5. We simplify the equation in terms of 11 and 13. Then we find x is equal to 2214, y equal negative 1845. To find x and y equation, we need to list all information that we get. we need to substitute information into the formula given. Find positive solution. X is greater than 0 and y is greater than 0. We need substitute X with X equation, then y with y equation. Then we can find t is greater than negative 201 and t is less than negative 142. Next, we can sketch the graph from t that we calculate. From the graph, we know the equation has unit solution.